Hi, Miss Venable here, bringing you a screencastify presentation on electron configurations and orbital filling notation. So we're going to get started with a little review of different models of the atom. These days, we know that the atom has protons, neutrons, and electrons. The nucleons in the nucleus are the protons and the neutrons. And we know that there are different isotopes of the elements, and we can write those in isotope notation showing the nuclide or what's in the nucleus. But there are lots of different models of the atom that have come over the years. Not all of those particles were known about from day one, and so we're going to talk really quick about models of the atom and how that all happened. So protons have been known about for a really long time. They were able to detect the positive charge in the nucleus, and so the first model that we're sort of interested in was from J.J. Thompson, and that was called the Plum pudding model or the chocolate chip cookie model, depending on who you are. And in this model, the positive charge, there is no nucleus. The positive charge part is just the cookie. And then they knew about electrons, and so the electrons are like the chocolate chips in the cookie. Or you can think of the positive charge as the pudding, and the electrons as the plums in the pudding. So that was the plum pudding model. Notice there aren't any protons, really. They knew there was some positive charge, but they didn't know there was an actual particle of protons there. And they knew nothing about neutrons, because neutrons are neutral. They're really hard to detect. So along came the Rutherford model. Now, Rutherford had a famous experiment called the gold foil experiment. And what he did was he shot alpha particles. Alpha particles contain 2 protons, 2 neutrons. It's really a helium nucleus. And he shot alpha particles at a very thin sheet of gold foil, so thin that some of the alpha particles were able to go right through the gold. But every once in a while, one of those alpha particles would hit the nucleus of the gold and kind of deflect an angle, or even just bounce straight off. And so what Rutherford kind of figured out was that, well, that alpha particle must contain something positive, because if it didn't, then it wouldn't be repelling away from the nucleus of the gold atom. So he came up with this idea that at the center of the atom is a small, dense core called the nucleus, and in that there is positively charged protons. So this model of the atom kind of developed later on into the Bohr model that we use today. And of course, we do know that there are neutrons. Neutrons were discovered by a man named Chadwick that add mass into the nucleus. So most of the mass of the atom we use today is collected in the nucleus, and then the electrons are distributed on the outside. They are negatively charged, but they don't take up a lot of space individually, but in terms of the cloud that they create, it is quite big. So in the Bohr model, based on emission of light from a hydrogen atom that is moving through energy levels, the atomic spectra we see from that emitted light is able to be diffracted by something like a diffraction grating, and we can actually track where the energy levels are and what the movement of the electrons through the energy levels is. So the emission spectrum is really proof for this Bohr model that we've been talking about in the class so far. And the Bohr model is great, but it kind of has some drawbacks. You can't really describe larger atoms using the Bohr model. We did a simplified Bohr model where the first energy level could hold 2 electrons and the second energy level could hold 8. And then we kind of said 8 for the third energy level, but we never really went past, that. And that's not actually legit how the Bohr model works. There's actually some overlap of energy levels, and there can be a lot more electrons in some of those higher energy levels. So we need a little bit more sophisticated model of the atom. And now in this unit, we're going to learn about the cloud model. It's also called the modern model or the wave model. Sometimes it's called the quantum mechanical model because it was based on the work of some quantum physicists. So in this modern model, let me get back to the word, instead of the electrons tracking around in orbits like the planets orbit the sun, instead what we have are electrons that occupy a cloud. And the clouds can have different shapes, but each cloud is in a certain energy level. Now let me give you a name because clouds is not really what they're called. They're really called orbitals. They're electron orbitals. So electrons are located in these orbitals, and an orbital is just a region of space where you would statistically be likely to find an electron. The thing with this is you can't really know exactly where an electron is because they're moving so fast, they're just a blur, and it's the blur that kind of makes this cloud thing. Think about like spokes on the bicycle wheel. When the bicycle wheel is moving really fast, the spokes look like a solid cloud. Same thing here. The electrons are moving so fast, they look like a cloud. But there's a lot more to it than that. So let's dive into this cloud model. And I'm going to teach you guys how to locate an individual electron. It's called an electron configuration. And I'll also show you guys how to do an orbital filling notation to show exactly how the electrons fill in the orbitals. Now keep in mind, in this cloud model, there's really no difference in the nucleus. It's the same old nucleus we've been studying. It's got the protons, it's got the neutrons. The strong nuclear force holds it together. You can have varying masses to create different isotopes, but basically the nucleus is known about. Okay, the only thing different about this cloud model is the electrons. Okay, so let's get into the cloud model. Principal quantum numbers. We used to call these energy levels. And honestly, I will still call them energy levels. But remember, we always designate energy level n equal 1 as the lowest, or what we call the ground state energy level. And then any of the other energy levels moving outwards are going to always contain electrons that have a higher energy. So you would have n equal 2, that's the second energy level, n equal 3 is outside of that, n equal 4, n equal 5, n equal 6, and so on. So when we say principal quantum number, what we're saying is that n value, like the principal quantum number for the first energy level is 1, because n equals 1. So it's just another way of designating energy levels, just like in the Bohr model, really. Okay, now here's where things get a little more interesting. Okay, within the energy level, there are sublevels. Okay, energy level 1, principal quantum number 1, has 1 sublevel. Energy level 2 has 2 sublevels. Energy level 3 has 3 sublevels. Energy level 4 has 4 sublevels. Okay, and the sublevels consist of orbitals, these clouds, and these clouds have specific shapes. So you can have an s orbital, and that will be a spherical orbital. You can have a p orbital, and it'll actually, there'll always be 3 of those orbitals together, and they're kind of dumbbell shaped. They kind of look like a little dumbbell. And the d sublevel has 5 orbitals. They're clover leaf shaped, if you guys know what a clover leaf looks like. The F sublevels have 7 orbitals, but they all have weird shapes, and we're not going to name those. Okay, let's look at those shapes. So an s orbital, the one sublevel would have an s orbital, and it's always spherical. It can hold 2 electrons. Now, in this cloud, we don't know exactly where the electrons are, but in this cloud, it can hold 1 or 2 electrons. It's full when it has 2. And what will happen is 1 electron in the cloud will be spinning one way and moving around really fast. The other electron in the cloud will spin in the opposite direction. It'll move around really fast. So the 2 electrons have opposite spins in that orbital. And that's true of all the orbitals. All orbitals hold 2 electrons, and they'll spin in opposite directions. That way their angular momentum kind of cancels out. Okay, there are 3 possible p dumbbell shaped in the p sublevel. There are 3 dumbbell shaped, and they kind of look like this. It's just a dumbbell shape that's oriented in different axes. Each one of those clouds can hold, each one of those orbital clouds can hold 2 electrons. So maximum number of electrons for this sublevel, the p sublevel would be 6. Okay, 6. I don't know what 6 is. 7, 6. 6 electrons for p's. Let's look at D's. D's are the clover leaves, and you can see all these clouds kind of have like 4 little lobes. So each of those 4 lobed clouds can hold 2 electrons. Since there are five orbitals possible for a p sublevel, that means we can have a maximum of 10 electrons. 10 for the Ds. Okay, and last one is the Fs. We're not going to name the shape because they're all a little different, but these are this is the F sublevel, and its orbitals are sort of weird. Can I just call them weird? The weird shaped ones. No name specified shape. But there are 7 of them, and since they each hold 2 electrons, that will give us a maximum of 14 electrons for the F sublevel. Okay, a little summary here. So S spherical, 1 of them. P dumbbell, 3 of them. D cloverleaf, 5 of them. And if you can get the F in there, there are weird shape, no name, and there are 7 of them. And each of those can hold a maximum of 2 electrons. So here's a little summary chart of the maximum number of electrons. First energy level has an S sublevel only. Of course, that would only be that one spherical orbital that we saw, and it can hold 2 electrons. Second energy level will have 2 sublevels, always starting with S. It'll have an S and a P. The S will be spherical. The P's will be the dumbbell-shaped orbitals. And so that can hold 2 in the S and 6 in the P's, which makes 8 electrons total. The third energy level, remember, has 3 sublevels, so S, P, and D. The S is spherical. It can hold 2 electrons. The P is the dumbbell shaped. It can always hold 6 electrons. And then the D, remember, there are 5 orbitals for that. So that means that it can hold 10 electrons. So adding all those up for the third energy level makes a total of 18 electrons. And then the fourth energy level will have 4 sublevels, S, P, D, and F. So S has the 1 spherical orbital, which can hold 2 electrons. P has the 3 dumbbell-shaped electrons, which can hold 6 electrons. D has the 5 cloverleaf-shaped orbitals that can hold 10 electrons. And F has the 7 no-name shaped orbitals that can hold 14 electrons. So adding those up makes a total of 32 maximum electrons. So this is pretty different than the Bohr model, because we never got these 8, 18, 32 situation going on in the Bohr model. So this is pretty different. Okay, I've explained the maximum number of electrons in the chart, but just so you guys remember, the maximum number of electrons in the first energy level is 2, and the second energy level is 8, and the third energy level is 18. And if we went all the way to the fourth energy level, just to recall, we'd be at 32. Okay, so what I would like for you guys to be able to do to demonstrate your mastery of the cloud model is I would like for you to be able to track the presence of electrons. And remember, electrons don't like to be in the outer energy levels. If they're a little bit unstable when they're in the outer, they always fill in the lowest energy level possible first. So this little chart I'm going to show you is going to help us keep track of the filling of electrons into energy levels. And so as our atoms get bigger and we get more electrons, we need to show the way it fills in those energy levels. And so you guys are going to need to be able to make this chart, okay? This is a chart for electron configurations. Let me make it really big for a second. Really, it's not going to get big. Okay. And notice that everything here in purple, this whole purple column, they all start with 1, 2, 3, 4, 5, 6, and they all have S's. Okay, so to help you remember the orbital filling, I always make this little chart. It's the diagram for the electron configuration, the filling in the electron configuration. Okay, second column, again, starts 2, skip the 1, 2, 3, 4, 5, 6, and so on, but these are all P's. The third column starts at energy level 3 with 3D, so these are all D's, and the fourth one is F, and then we don't really have to draw the G's. I don't know why they did G's there. Okay, and then what they've done is they've put diagonal lines through these. Okay, so the first thing that fills in is the 1s sublevel. And if I go back up to the top, the next thing that fills in, I follow this diagonal, is the 2s sublevel. Back up to the top, follow diagonal. The next sublevel that fills in is 2p, and then 3s, and back up to the top. And the next sublevel that fills in will be 3p and 4s. So this is just showing you the order. Now, it does get a little bit weird. It does. Because there's some overlapping of sublevels. And if we were to draw out the clouds, what we would see is that the 3d energy level electrons are actually a little further out than the 4s. You would think the 4s would get bigger because it's a higher principal quantum number, but no, it actually has a little less energy. So the 4s sublevel gets filled up before the 3d sublevel. And so that's why we have to have these little diagonal lines to follow the order. Okay, all of these also correspond to the periodic table. So on the periodic table, if an element is an alkali metal or an alkali earth metal, including hydrogen, it's in what we call the S block. So these first two columns here are the S block. And what that tells me is the ending sublevel. What is the maximum sublevel that could be full? So let's look at calcium. Okay, calcium's right here, and its atomic number is 20. Excuse me, it's right here. Its atomic number is 20. And since it is in the second column of the 4s row, then that tells me that the ending configuration will be 4s with 2 electrons in that s orbital, and we'll put a little 2 superscript to indicate that. All right, these here on the right-hand side are the, oh, by the way, this helium right here is also an S. I know it's over here with your noble gases because it is a noble gas, but in terms of atomic orbital notations and electron configurations, helium would be 1s with 2 electrons. So we would put a 2 superscript for that one. Okay, the P block over here is going to be all of your boron family, carbon family, nitrogen family, oxygen family, and so on. So let's say you have the element sulfur. Okay, sulfur is right here, and it's in the 3p row. It's in the P block, and it's in the third row, so it's in the third period. So the principal quantum number is 3. It's in block P, and if I count over from the left, this would be 3p with 1 electron. This would be 3p with 2 electrons. This would be 3p with 3 electrons. And sulfur is going to be 3p with 4 electrons right here. And so the way I'll designate its very last energy level is I'll write 3 and then p. And then as a superscript, I'll say how many electrons are in that p sublevel. So there will be a superscript 4. So it would be 3p4 will be the last sublevel if I wanted to write the sulfur atom. Okay, the D block is a little weird. That's because of the overlap I was telling you guys about. Because the 4s energy level is actually a little higher or lower, than the 3d energy level. So a little something weird happens here, and I've circled it because the 3d row for the D block, the blue block here in the middle, is actually in the 4th period. So this should be a 4. All of these should be 4, right? But it's not. It's 3 here. And then it goes 4, 5, 6. So the rows get a little scattered. In our classroom periodic table, I actually put like a little yellow sticky note right at the top of this D block here, just to remind people it starts with 3D. The F block elements are down here. And again, there's all that overlapping that happens. So this row starts with 4F and this row starts with 5F. So just looking at the periodic table, if you guys will memorize the block system here, if you're looking at the periodic table, you're going to be able to tell me what the very highest sublevel will be for any atom. And that's a lot of fun because you can check yourself. Okay, now there is a shortcut to electron configurations, and that is noble gases. Let me go back to this. Noble gases are always the 6th element in a P block, which means they typically end with a P6. And we can kind of take advantage of that because everything that comes after that would start with a 4 or 5 or 6 and always be an S. So here in this third row here, I've got the noble gas argon right here. Okay, and it's going to end its electron configuration 3p6 because all the noble gases end in p6. They're always the 6th element in the blocks. And so if I wanted to use that as a shortcut notation for anything that comes after it in the next row down, I can. I just have to put the argon in brackets, and then I can pick up my configuration looking at the next row. So the next block to fill would be 4s2, and then the next block to fill would be 3d. It could go up to 10. Let's say I wanted to do the shortcut notation for zinc. Okay, zinc is right here. It's the very last element in the 3d row. Zinc is right here. And so I could just use argon in brackets as a shortcut, and then I just write whatever comes in the row before it, which would be 2, so 4s2 electrons possible. And then 3d, and since zinc is the 10th element in the 3d row, I would put a 10 superscript, on the d. Pretty cool. So that's a little shortcut notation, and I'll do an example for you guys. So the full configuration for phosphorus would end with 3p3. Okay, so I'm following these little arrows. 1s2 can hold 2 electrons, 2s can hold 2 electrons, 2p can hold 6, 3s can hold 2 electrons. Remember, s orbitals can only hold 2. And when I get back up to 3p, it won't be full. It'll only need 3 electrons. P's are full with 6, but this is full with 3. So the stuff in blue here, all the way up to 2p6, is actually the configuration of the noble gas that comes after phosphorus. Okay, so let's find phosphorus. Phosphorus is right here on the periodic table. Okay, it's in the 3p row. And if you look at the preceding noble gas, the noble gas that comes before it would be right here. That's neon. Okay, and its configuration would end with 2p6. So instead of having to write all that stuff that comes before neon, what I can do is just put the neon in brackets, and that takes care of the first part of the configuration up to neon. And then I just have to put whatever comes after neon. So what would come after, I'll go back here. What would come after, so there's neon, and then what would come next would be this 3s sublevel. Okay, and then I would have the 3p, and phosphorus would be in the third block, so 3p3. So that's the shortcut notation. I got the 3s2, and then I got the 3p3. I like that shortcut notation. On really big atoms that you're trying to write a configuration for, it saves you a ton of time. Okay, orbital filling. Orbital filling is a little bit more complicated. It includes the idea of electron configurations, but then it also shows you the spin of the electrons in the orbital. Remember when I told you guys that one electron spins up and one spins down in the same orbital? So it'll show you the spins. The other thing that it shows you is the energy levels of the electrons. If you do the orbitals stacked, like I've done them here, as you go higher, it's showing you clouds of electrons that have more energy in them because they're further away from the nucleus. And so we'll always kind of start at the bottom of this chart, and we'll put an up and a down arrow in each orbital. Now, there are some rules for orbital filling. The first one I've already taught you, which is the off-ball rule. We mentioned it. We saw it, but we didn't mention it. So let me go back. The off-ball rule says that electrons have to enter the lowest energy level first. So that would start with the 1s sublevel, and then the 2s sublevel, and then the 2p, and then the 3s, and the 3p, and the 4s, and the 3d, and the 4p. Basically, that means I have to follow this diagonal line. Okay, you'll need to know that order. You'll need to know the order of the sublevels. So teach yourself how to make this chart and draw the diagonals, or just memorize the order of the sublevels. So what I've done on the orbital filling chart is I've started at the bottom, and if it's an S sublevel, I drew one box because there's only one spherical orbital. If it's a P sublevel, then I drew 3 boxes because there are 3 dumbbell-shaped orbitals. Remember that. And if it's a D sublevel, I drew 5 boxes because the D sublevel can have 5 cloverleaf-shaped orbitals. So the number of boxes correspond to the clouds for the orbitals. Okay, and what we're going to do is fill in the chart. Now, I could write this out horizontally, but I'll need to do it in the exact same order that I wrote the electron configuration. So this is the kind of more vertical, stacked up looking way, and then left to right here is it written out horizontally in order of energy levels. So here are the rules for filling in these orbital filling diagrams, okay? We already know the Aufbau principle. Electrons have to go into the 1s, and then the 2s, and then the 3s, and then the 3p, and so on. The next one is called the Pauli exclusion principle. It says an orbital may hold a maximum of 2 electrons. One spins up, one spins down. And we'll use arrows to represent the up and down spins when making an orbital filling diagram. So an orbital may hold a maximum of 2 electrons. And all of the electrons in one sublevel will always point the same direction first. In other words, draw your ups and then do your downs. The last rule is called the Hund rule. Sometimes I call this the bus rule, I guess. And what that says is that when you have, let's say you have 5 electrons and you want to fill in a D sublevel. Well, a D sublevel can hold 10. So how am I going to show that? Well, I'm not going to put 2 electrons in each orbital because that would leave empty orbitals at the end. What you're going to do is fill every orbital with 1 electron and then go back and pair up your electrons with the opposite spin. So that will leave a lot fewer empty sublevels. Okay, let's look at phos. I'm doing phosphorus today. I don't know why, but phosphorus is atomic number 15. It should have 15 electrons. And if I look at the electron configuration and I count 15 electrons in order, there's going to be 2 electrons in the 1s energy level because it can hold up to 2. There's going to be 2 electrons in the 2s energy level because it can hold up to 2. It's an S. In the P sublevel, that has 3 orbitals, so it can hold 6 electrons. And then in the 2s sublevel is a spherical sublevel with a S-shaped or spherical orbital. It can hold 2 electrons. So 2 electrons there. And then the P, the next one is the 3p. It can hold up to 6, but remember, I only need 15 electrons. So if I count my electrons, here I have 2, here I have 2, here I have 6, here I have 2. Okay, so that adds up to be 12. So I don't need this P sublevel to be full. I only need 15 electrons, so I only need 3 more. So remember, phosphorus ended with 3p3, right? We talked about how that periodic table, where it is in the block, 3p3, right there is where phosphorus is. It's the 3rd element over in the 3p row in a p block. So I should have known how phosphorus was going to end without even having to write it. But knowing that you have 15 electrons can also help you write this. Okay, so there's the electron configuration. I always write that first. Okay, then I can do my orbital filling and show the ups and the downs and the spins and where exactly they are in which orbitals. So you're going to start here at the bottom. You're going to fill your 1s sublevel. You're going to do an up arrow. That's your spin up electron. And then right next to it, you're going to do a down arrow. Then that sublevel is full. So you're going to go to the next sublevel, the next highest energy sublevel, which will be the 2s sublevel. And you're going to fill it with an up spin electron and a down spin electron. Okay, and then that's full. And then next in terms of energy is 2p. Okay, so in this time, we're going to do all the ups first. Okay, so remember, we can fill 6 electrons in a p sublevel. So we're going to go up, up, up. Think about the clouds, right? You always have 3 clouds. You're going to put 1 electron in each cloud, and then you're going to go back and do the down, down, down. So that'll be the part going up. Okay, so that'll be full. 3s sublevel can hold 2 electrons, so up, down. And then we get to the 3p, it's going to look a little different. Okay, remember, we only have 3 electrons in the 3p sublevel. So what you're going to do, according to the Hund rule, okay, sometimes it's called the subway rule or the bus rule, because when you get on the school bus in the morning, you don't want to sit right next to somebody. Okay, everybody spreads out. You don't double up with somebody in a seat until all the empty seats are full. So same thing with these P's and D's and F's sublevels. Separate out the electrons as much as you can. Do all the ups first before you match them with downs. So we only need 3 electrons, so we're going to do up, up, and up. All right. So here's how it's going to look when it's all filled in. And notice this P sublevel here has up, up, up. That's your 3p3 sublevel. Okay, couple of little weird things. Transition metals have that weird overlapping thing that happen, right? Like when we get into 3Ds and 4Fs, there's all this overlapping of sublevels. And I kind of wanted to touch on like what's going on there. So transition metals kind of have a unique ability because these overlapping sublevels are so close to each other. They kind of have the ability to do something unique, and that is they can promote electrons out of an S sublevel into the higher D sublevel. I know that's pretty freaky, but they have that ability, and the objective of doing that is to fill or half fill that D sublevel because that promotes the stability in the structure of the atom. They want to fill it or half fill it. So for a D sublevel to be half full, it would need 5 electrons, 1 for each orbital. For it to be completely full, it would need 10 electrons, right? So each orbital would have an up and a down. And so what it's able to do, what transition metals are able to do, is in order to achieve a configuration where they have full or half full outer D sublevels, is they'll kick an electron from the 4s, or maybe even 2 electrons, okay, from the 4s, and they'll promote them up to the 3D. So notice here, I've taken an electron away. This is copper, by the way. And I've taken an electron out of the 4s sublevel, because it used to be 4s2, and I've promoted it into the D sublevel. So now instead of 3D9, it's actually 3D10. So that's kind of cool. So copper and chromium both have this ability. Copper ends up with a completely full 3D sublevel, and it really likes those full sublevels. Chromium kind of does the same thing, but it ends up with a half full D sublevel. So 5 would be half full. And the only two you guys would even need to know are the chromium and copper. Okay, let's look at chromium. Here's the orbital configuration. So here's the configuration without any promotion. Notice that the 4s sublevel here has 2 electrons. The 3D sublevel here has 4 electrons. That's pretty unstable. Okay, all the lower ones are full, but this outer kind of weirdness makes it a little bit unstable. And only transition metals, and only a few of them, have this ability. So what the chromium does is it's able to promote. So it's going to promote an electron out of the 4s lower energy level into the 3D level, which is a little bit higher. And now there's only there's a half full 4s sublevel, and then the 3D sublevel will also be half full. So that makes it a much more stable configuration. Okay, and I'll let you guys figure out the electron configuration for that. Oops, nope, I told it to you. There it is. So it would end with 4s1, 3d5. Copper kind of does the same thing, but it's going to end with 3d10. So I hope that helps you guys get started on electron configurations and orbital filling notations, and have fun doing this chemistry with the cloud model. Thanks so much. Bye.